Oh. All right, good morning, everyone. I hope you're having a good morning and we'll have a good rest of the day. So, let's see, normal stuff, homework due on Friday, whoops. If you haven't done your lab already, make sure you do pre-lab 3 before you show up to your registered lab section. And then the last thing I wanted to remind you of is that we do have our midterm coming up. It's going to be on Wednesday, February 28th. And that is, so it's Wednesday today, obviously. So we have today's class and then we have Friday's class. And then it's the reading week. So there's no classes next week. We'll have a class on Monday after the reading break. And then Wednesday we'll have the midterm. I posted details about the midterm on the course website, so you can read about them there. But it's going to cover material that is up to and including chapter 7, which we're doing right now. In fact, what I expect is that we will finish what we're going to do of chapter 7 today, and I'll try to mark in the notes where the cutoff of material for the midterm is. So we'll finish chapter 7 today, and we'll get a start on chapter 8, but the chapter 8 stuff will not be on the midterm. The midterm will be in person, so you have to come to class and write it here with a pen and paper, so it's not a prayer learn thing. And I'll talk more about the format maybe on, well, why don't I just talk about it now? So the format will be probably just 2 multiple choice questions at the beginning, and then there'll be like 3 long answer questions where you can write out your solutions, and then even if you don't get the exact right answer at the end, you can pick up part marks along the way. So if you show your work, and if you know, the cutoff is going to be up to and including chapter 7. So that means it will be chapters 5, 6, and 7 is the stuff that will be covered. But there'll be more emphasis on the material that came after the first quiz. And so that's primarily chapters 6 and 7. So that's what the emphasis is going to be. I'm not going to say that you don't need to know anything from chapter 5 because that would be silly. But I'm going to focus on the chapters since that first quiz. Right. Any questions about that? Not seeing any. Okay, good. So what we've been talking about recently is the relationship between electric potential and electric field. And I want to do one more thing. We talked about conductors and electric fields already, and we learned a bunch of things. We learned that for a conductor in equilibrium, one is that the electric field inside the conductor has to be zero. And that's because what equilibrium means is that there's no net flow of charge inside a conductor. The charge is just moving randomly, but the distribution is not changing. If there was a non-zero electric field inside the conductor, it would exert forces on the charges that are inside the conductor and free to move around. And so they would all flow in a common direction, and that would violate our definition of what equilibrium means. Likewise, at the surface of a conductor, the electric field has to intersect that surface perpendicularly. And the reason was, if we had an electric field that wasn't perpendicular, it would have a component parallel to the surface, and it would cause charges at the surface to flow in a common direction, again, violating our assumption of equilibrium. So E is zero inside, and E intersects the conductor at a perpendicular. And then there was one more property, and that was that all excess charge on a conductor resides at the surface. And we thought about that in two different ways. One was just do Gauss's law, to do like a formal proof of that idea. The other more intuitive way is just to say, well, if I had some excess charge on a conductor, those charges are free to move around. They're not going to be concentrated near the center because there would be a strong Coulomb repulsion between those like charges. And so they move as far as they can away from one another so as to minimize that repulsion. So they all sit on the surface. What we haven't done is we haven't talked about conductors and electric potential. And so that's what I want to start with today. So we could find the electric potential difference between 2 points, 1 and 2, by evaluating this kind of integral, this E dot ds. This came ultimately from the work kinetic energy theorem. So let's imagine we do that for our conductor. Let's say we're inside our conductor at point 1, and then we're going to follow a path to some other point 2. And I don't really care what the shape of that path is. It could be whatever you like. I'll draw it as a straight line path. So if we were to evaluate this integral for this path from 1 to 2 inside of our conductor, we would say, well, delta V is equal to the integral from 1 to 2 of E dot ds. I've just rewritten the exact same expression, but because our 2 points are inside the conductor, the electric field has to be 0. Okay, so our points 1 and 2 are inside the conductor, where E is equal to 0. Okay. But delta V is the change in potential. So it's the final potential minus the initial potential. Our final position is at position 2. And so delta V is just equal to the potential at 2 minus the initial potential, which is our starting point, 1. And then all of that has to be equal to this integral. But inside the integral, in the integrand, is the electric field, which is 0. And so this has to be equal to 0, and therefore V2 is equal to V1. So there's no change in potential as we move from 1 to 2 in our conductor. And there's nothing special about the positions I chose for 1 and 2. I could have put 1 and 2 anywhere at all inside those conductors, and I could have chosen any path between those 2 points, and the result would be the same. We would have no change in potential. V2 is equal to V1 wherever those points are, as long as they are inside the conductor. So for any 2 points inside a conductor in equilibrium, we will find that delta V is equal to 0, or V1 is just equal to V2. And so therefore, the potential inside a conductor in equilibrium is constant. Okay, and so that's the results that we wanted to get for our conductors. So notice that I've specified that the conductor has to be in equilibrium. A few weeks later, we'll start talking about little circuits. So we'll take some wires and some batteries and maybe some resistors, and we'll connect them up and we'll get some current flowing in our little circuits. And so current is going to be like this flow of charge around a closed loop. And so that is clearly not in equilibrium because we have a net flow of charge in some common direction. So when we start talking about circuits and the wires in our circuits, those are going to be conductors, but not in equilibrium. And so you don't have to have a common uniform potential in that case. But for what we're talking about right now, it is true that the potential everywhere inside a conductor in equilibrium is going to be constant. A common mistake that's made by kind of people introduced newly to this kind of concept is that they think that the potential has to be 0 everywhere in a conductor, and that's not true. It just has to be constant. It could be any value. It might be 0, but that's definitely not required. So let's just make a note of that. Notes. The potential in the conductor is constant, but it does not have to be 0. Okay, good. So what we're going to do is let's do one more example, and that's actually this last example is going to wrap up chapter 7 for us, and then we'll transition into chapter 8. So here's the example. Let's consider a pair of large parallel plates. What we're actually doing is we're going to start talking about capacitors. And capacitors are going to be devices that we can use to store charge. They're becoming pretty important. Like if you were to, for example, smash open your phone or your laptop or whatever, it's going to be full of capacitors. In fact, you know, people are trying to transition away from fossil fuels and to cleaner energy sources. And one of the challenges is that, for example, if you use solar panels or something like that, you know, you have hot sunny days where you generate a lot of power. And then you have other days where it's cloudy, overcast, and raining, and you're not generating much power. And so what you'd like to do is you'd like to be able to store some of the charge that you create during the hot sunny days and save it so that you can use it when it's raining. And so one way to do that is to construct these large banks of capacitors to store charge. And so we're going to start talking about the fundamental physics of capacitors. Okay, so we're going to have these two large parallel plates with equal but opposite charge. In fact, we'll say that they have a charge per unit area is going to be sigma. Okay, so if a plate has a charge Q, then sigma is Q divided by whatever the area of that plate is. Okay, so I'm going to draw this from a side view. And so on the side view, we'll just see the edge of the plates. And so we've got one plate here, and then one over here. And we'll make this one our positive plate. And we'll make this one our negative plate. And what we know is that we're going to have an electric field that points from the positive to the negative. Okay, so something like that. In fact, we've drawn this before, and if you remember, we said that if you have a large flat surface with a charge per unit area sigma, it creates an electric field that's equal to sigma divided by 2 epsilon. It's a simple result. So the positive plate makes an electric field equal to plus sigma over 2 epsilon naught. The negative plate makes an electric field equal to minus sigma over 2 epsilon naught, and the net electric field is due to the sum of those two. And if you recall, or if you look back in our notes, what we found is that the electric field would be 0 outside the plates because the contributions from the positive and negative plates exactly cancel in that region, but they add between the two plates. And so what we can do is we can summarize, let's just make a little summary. Each plate creates an electric field of magnitude or strength. E is equal to sigma over 2 epsilon naught. Whoops. And so outside the plates, the two contributions cancel, and they add between the plates. Okay, so if they add, you just take this contribution sigma over 2 epsilon naught and multiply it by 2, and so that cancels that factor of 2, and so the electric field between these two plates is equal to sigma over epsilon naught. And let's it's a vector, so let's assign a direction. Let's place an x-axis over here. So this is going to be my x-axis. I'll put 0 over here, and I'll put D over here. And so the electric field, the way we've defined our coordinate system, is directly along the direction of the x-axis. And so that is usually the I-hat direction. It's the notation we use. Okay, so fine. This is everything we've done already. We've seen all this before. So what I want to do now is I want to ask the question, what is the potential difference between these two plates? And so the first question is, A, if the plates are separated by a distance, what did we use? We used D. Let's find the potential difference, delta V, between the two plates, the pair of plates, let's say. Okay. Well, that's relatively easy to do. One way to do it is to say, look, I know the electric field is constant between these two plates, it's uniform. And so we wrote down previously that if you have a uniform electric field in the direction of the displacement, the potential difference is just going to be equal to the electric field times the distance moved. And so we could anticipate that it's just going to be E times D, but let's work it out and let's see if we can confirm that result. So what I'm going to do is I'm going to start over here at the positive plate. We'll call this 1. And we'll follow a path parallel to the electric field. And we'll end up over at the negative plate. That will be 0.2. And our displacement vector ds is along this direction. It's along the dashed line parallel to the electric field. Okay, good. So delta V is equal to minus the integral of E dot ds. So we know that E is equal to sigma over epsilon naught times I hat. And ds, the way we've constructed this displacement vector, is it's exactly along the x-axis. So I'll say our size of our steps is going to be like this dx, and it's a vector, so we have to give a direction, and so it's in the I hat direction parallel to the x-axis. So what we have to do is we have to evaluate E dot ds. And so let's do it slowly. We'll do it in a bunch of steps. So there's E, and then we have to take the dot product with ds, which is dx I hat. Okay. One way to rewrite this is to say, well, look, I've got a bunch of constants, sigma and epsilon naught, and this dx. And then the dot product really is just acting on the vector part. In this case, the vector part are these unit vectors I hat. So I hat is going to be the magnitude of I hat times the magnitude of I hat times the cosine of the angle between them. But they're the same vector, so the angle between them is 0. And the cosine of 0 is going to be 1. And so this is going to be the magnitude of I hat times the magnitude of I hat times the cosine of 0. But a unit vector has length 1, and cos of 0 is 1. So all of that stuff is just going to be a 1. Okay, and so the dot product just evaluates to sigma over epsilon naught dx. And that's very nice because now we've gotten rid of all the vector part of this expression or this calculation that we're trying to do. So then we could say, therefore, delta V is equal to minus the integral. So E dot ds, we've simplified. So that's just going to be sigma over epsilon naught dx. And we're going to go from position 1 to position 2. Okay. The sigma and the epsilon naught are both constants, and we can always take constants outside of our integral. And so this is going to be equal to minus sigma over epsilon naught and then it's the integral from 1 to 2 of dx. Okay, let's go back and look at our picture here. We're going to go from 1 to 2 along this x-axis, and so all we're doing is we're adding up all the little steps that take us from 1 to 2, and that's just equal to d, the distance between the plates. So I walk along that line, and the total distance that I walk is just d. So what we have here is d, and so therefore delta v, which is the final potential minus the initial potential, is equal to, we have a minus sign, sigma over epsilon naught times d. Okay, and what we should do is we should make sure that this result makes sense. Last class, one of the things that we discovered is that electric fields point from high potential to low potential. So if we look at our picture, our electric field is pointing to the right. So it must be that the positive plate is at a high potential and a negative plate is at a low potential. So that the difference of the potential at 2 is the low potential minus the potential at 1 is high potential. That should come out to be a negative result. And that's exactly what we found here. So since delta V is negative, it's less than 0, it must be the case that, let's see, V1 must be greater than V2, and V1 is at the positive plate, and V2 is at the negative plate. And so this is consistent with our previous observation that electric fields point from high to low potential. Okay, good. So that's what I wanted to cover from chapter 7. This is the cutoff for the midterm. So midterm cutoff. Does anybody have any questions before we start talking about chapter 8 material, capacitors? All right, good. So then what we're going to do is we're going to do OpenStax University Physics Volume 2, Chapter 8. And the main focus is going to be on capacitors. Okay, and this last example is kind of been used as a bit of a segue for capacitors, because the most common geometry for a capacitor is exactly having these two parallel plates. Now, when you're making electrical devices, what you'd like to have is you'd like to have your devices as small as possible, because I want to cram them inside this little phone that I can put in my pocket and carry around with me. So if I want a large capacitor, I don't want to have these huge parallel plates that I have to kind of assemble. So what they do is they take these like little foils, like imagine taking some aluminum foil, 2 sheets of them and putting them like right on top of one another. But then we put like a thin layer of some insulating material, like maybe a piece of paper. Okay, so we have these 2 aluminum foil conductors separated by a piece of paper, but it's this big, broad, flat object. And then what we do is we start rolling it into a little coil. And if you do that, you can have these large areas that are parallel to one another, but occupying a smaller kind of volume. So people are looking for tricks to try to shrink down the size of these electronic components. Okay, so a capacitor is made from a pair of parallel conducting sheets with equal but opposite charge. Okay, and so, we've just analyzed this thing. And so I'll draw it again. I'll draw this side view. And let's say they're separated by a distance d. So we already know then that the potential difference is going to be just whatever the electric field is times d. So let's keep that in the back of our mind. So the definition of capacitance is the following. We're going to use symbol C for capacitance, and it's going to be the charge Q. So let's say we put charge Q on the positive plate and we put charge minus Q on the negative plate. So then you just take Q, the absolute value, so a positive quantity, and we divide by the absolute value of the potential difference. So capacitance is always a positive number. Okay, so it's the absolute value of the charge divided by the absolute value of the potential difference between the two plates. Okay, so before we go work out an expression for the capacitance, let's just worry about the units. So the units of capacitance is equal to the units of charge Q divided by the units of potential difference, delta V. And so this is charge is measured in coulombs. Delta V, potential difference. We did some unit analysis of that last time, but it's so common that they define potential difference to be measured in volts. So it's capacitance is measured in coulombs per volt. You know, in E&M, they define a lot of units. And so the capacitance has units of coulombs per volt, which is defined to be a farad, which is just the name of, I guess, the person who worked out a lot of these details. Okay, so the utility of capacitors is that they can be used to store charge. And what we're ultimately going to see is that eventually we're going to do things like connect batteries across the two plates of our capacitors. And so that's one way to charge them. Like I could charge them by taking a plastic rod, rubbing it with some, I don't know, felt. So I charge the rod and then I touch one of my plates. And then maybe that gives a positive charge on one plate. And then, you know, I figure out that, you know, if I rub some different type of plastic with some different type of material, I can put a negative charge on the other plate. That's one way to do it. But what's more practical is to take something like a battery, which provides a fixed voltage difference. That's what a battery does. So the little square ones provide 9 volts. The little AAA batteries that are now pretty common provide 1.5 volts. And so I could take the two terminals of my battery, connect one to one of the plates, one to the other plate, and that allows charge to flow from one plate to the other. And so I can get positive charge on one and negative charge on the next. So the question is, how much charge can I store for a fixed voltage difference? So for a fixed potential difference, say delta V, maybe that potential difference is provided by a battery. The charge stored by a capacitor is. Okay, so all we're going to do is we're going to go back to our definition of capacitance, Q over delta V, and just solve for Q. So we just multiply both sides by delta V, and so the charge stored is going to be equal to Q, oh shoot, sorry. So Q is equal to C times delta V. All right. So what that tells us is that if I want to store a lot of charge, then what I should do is I should make my capacitance as big as possible for whatever that fixed potential difference is provided by whatever battery it is. So then what I'd like to do is I'd like to know, like, what are the parameters that determine the capacitance? Like, how do I change the geometry of my parallel plates so that I increase C as much as possible? Okay, so let's find the geometrical parameters that determine C. Okay, so we'll go back to our definition. C is Q over delta V. Okay, we just calculated delta V in this previous example. So we just found, whoops, that delta V, if I take the absolute value, I'm not worried about this negative sign. So let's just take the absolute value. Well, what was it? We just did the problem. It's right here, sigma divided by epsilon naught times D. So we just found that delta V is sigma over epsilon naught times D. Okay, and we also know that sigma is the charge per unit area. So we also know that sigma is Q over A. So I'll draw more of a three-dimensional picture of our parallel plate capacitors now. So instead of a side view, let me draw kind of a view with a bit of perspective. So here's one plate, and then we're going to have a second plate that's parallel to it, and it's going to be something like this. Okay, so we'll make this one maybe a bunch of positive plates, a bunch of positive charge on that plate, and then over here we've got some negative charge on this one. So this is going to have area A. So both plates have the same area. So we'd have over here, we'd also have area A. Okay, so that means then that delta V is equal to sigma, but sigma is going to be Q over A. And then we have to multiply by D, and we have to divide by epsilon naught. So that's our potential difference. And all we're going to do is we're going to sub this into the definition of capacitance. So therefore, C is Q over delta V is equal to Q divided by, so delta V is Q D divided by A epsilon naught. We can cancel a factor of Q and then just rearrange this to make it look nicer so that, let's see, C is equal to, we have 1 over D over epsilon naught A. So the epsilon naught A comes up to the numerator. So we could write this as epsilon naught A divided by D. Okay, and remember D is going to be the distance between the two plates. And so there it is. So if we were interested in trying to store a lot of charge by having a large capacitor, what we should do is we should make the area of the plates as big as we can, and we should make the distance between them as small as we possibly can. Okay, so to make C large, we want the plate area to be big and the separation distance D to be small. Okay, now I won't write it down, and I'm not going to ask you this on a test, but there's some interesting things that we can think about. If I have two plates with a very large area, let's say, and let's say I put a ton of charge on them, like I put as much charge as I possibly can on them, then I can get very strong electric fields between these two plates. And what can happen is that electric field can get so strong that it can actually pull, say, an electron from the negative plate off of that negative plate across the gap and to the positive plate. And so that's called arcing, or like sometimes people call it like breakdown. And so you want to avoid that kind of breakdown. And one way to do it is to not have, say, air between your plates, but to have some kind of insulating material. So Teflon is an example of something that might be used. And the Teflon will prevent, or it will inhibit, this breakdown where you pull charges off one plate across the gap and onto the other one. Okay. All right. So let's see. What we're going to imagine then is that I want to imagine that we can use these capacitors as a component in some kind of circuit. And I'd rather not have to draw these 3D diagrams all the time. And so what we're going to do is we're going to develop some circuit symbols so that we can represent these components that we're developing in some abstract circuit diagrams. Okay, so circuit symbols. I should mention while we're at it that capacitors are not only used to store charge. So sometimes if you were to take, let's suppose you were to take a course in electronics. So if you became a physics major, you would take a second-year course in electronics, physics 231. And what we would discover is that capacitors can also be used to do things like filter signals. So let's imagine you're trying to build like an audio amplifier. And so what people can hear are in the frequency range. Well, who knows? Do people know, like, what are the range of frequencies that you can hear? Does anyone have any idea? What's the lower range? About 20 hertz, that's right. What's the upper range? 20 kilohertz. Yeah, about 20 kilohertz. So you all can hear better than I can. I'm old and I'm breaking down. So I can't hear the high-pitched stuff, but from 20 to 20 kilohertz, someone with good hearing can hear that range. And so maybe you're building an audio amplifier, and what you find is that you're amplifying also noise at other frequencies that is going to interfere with your signal. So maybe you want to have something that's going to attenuate contributions that are above 20 kilohertz and below 20 hertz. And so it turns out that a capacitor in combination with a resistor can be used as a filter, so it would pass signals from 20 to 20 kilohertz and attenuate others that are outside that range. But anyways, that's not for today. All right. The schematic symbol for a capacitor is, and it's an easy symbol, and it's one that makes a lot of sense. Okay, so this is the circuit symbol for our capacitor. While we're at it, let's do the circuit symbol for a resistor. Sorry, not the resistor, a battery. The schematic symbol for a battery is, it looks similar, but it's got these two horizontal parallel lines. One is shorter than the other. The long one is the positive terminal and the short one is the negative terminal. And so instead of drawing like some cartoon picture of a battery where this is positive and negative, we'll use this convenient little circuit symbol. And instead of drawing like actual parallel plates with some like perspective view, what we'll do is we'll replace them. Oh, sorry, that's not right. I didn't get off that. I want you to go down like that. Okay, and so there it is. So if I wanted to charge a capacitor, one way I could do it is I could take my parallel plates. I'll draw it kind of in this way first. Okay, so there's my parallel plates. And what I could do is I could add a wire to one of them and I could connect it to a battery like so. This is the negative and positive terminal of my battery. And I'll take my positive terminal and I'll connect it over here. So in doing this, what I could do is I could put some positive charge on the plate connected to the positive terminal and some negative charge on the plate connected to the negative terminal. And so this would work exactly well. They would be totally fine. And so what we're going to do, if I wanted to represent this with a schematic, the equivalent drawing would be for my capacitor, just these two parallel plates. And for my battery, I would have a positive terminal and a negative terminal. And this would deposit positive charge on this top plate and some negative charge on this bottom plate. Okay, so we have 5 minutes left. And so what I want to do is let's do one example. So the example is going to be the following. We take a battery of a known voltage, we connect it to our parallel plate capacitor, and then we get some charge on our plates. Then what we're going to do is we're going to leave the battery connected, and then we're going to pull the plates farther apart, and I want to know what happens to the charge. Okay, so example. A parallel plate capacitor is connected to a battery of, let's say, voltage delta V. The charge on the plates is plus or minus, let's say Q1. And we could calculate Q1, it's just going to be the capacitance times the voltage difference. Okay, so then next, with the battery still connected, the capacitor plates are pulled apart such that D goes to 3D. So we're triple the distance between the two plates. So what is the new charge? Say plus or minus Q2. All right, so let's draw our circuit. So we're going to have our battery. This will provide delta V. Here's positive and negative terminal. And then here's our capacitor plates. And we're going to have plus Q1 on the top plate, minus Q1 on the bottom plate. And let's just indicate that this distance between the two plates is D. And then what we're going to do is we're going to have the exact same battery, so plus minus, but now we're going to pull these plates apart And so this is going to be plus Q2, this is going to be minus Q2, and now this distance is 3 times D. Okay, so the first thing that we want to observe is that because the battery is always connected, the voltage never changes. So since the battery is always connected, delta V is the same in both cases. Okay, and we know that C is Q divided by delta V. So therefore Q is C times delta V. The other thing we know now is that C is epsilon naught A over D times delta V. And we'll call this Q1 because the distance in our first scenario is just D. So we're going to use C as epsilon naught A over D. At Q2 is going to be epsilon naught A over 3 times D. Then we get delta V. And so when we look at this, we can immediately see that Q2 is exactly 1/3 of Q1. And so this is equal to Q1 divided by 3. This makes sense because remember what we said is if we want to store a large charge, I should make my capacitance large. And I make my capacitance large by having big area and a small separation distance. So when I pulled the 2 plates of the capacitor apart, the area didn't change, nothing happened there, but we made the plates farther apart and that reduces the capacitance, which means it stores less charge. And so we found 1/3 of the initial charge. Okay, that's where I'm going to stop. If you want a little challenge, repeat this problem, but this time, before you pull the plates apart, disconnect the battery, and then pull the plates apart and see what changes. Okay, that's what we'll start with, I think, on Friday. All right, thanks very much.